All right, guys, welcome back. So we just had a really good discussion here. If anyone's heard of Gödel's theorem, you can take any arbitrary computer program and turn it into a number. If you take all the letters in your program and turn them into ASCII codes and then multiply them all together, you can actually perform your computing. You can run the program by doing various arithmetic operations on that giant number. And the question is, if you did that, would your calculator then be a computer? Because you could use Gödel numbering to run any arbitrary program. That's a really hard one. Go and look at Gödel's theorem, if you like that kind of thing. Okay, just to get us back into things then, I just wanted to give you a few current applications of different architectures, some of the things that I'm involved in with research work. So as you probably know, Lincoln is now the UK leader in agricultural robotics and agricultural technology more generally. We're leading a big project with Cambridge and East Anglia as our junior partners, so we're recognised as the UK centre of it and increasingly throughout the world. So we're very involved here with putting devices out literally in the field, in actual agricultural fields. We're very involved in putting embedded systems out there that sense things. We're putting systems on robots that go out and do agriculture automatically. We have a site a couple of miles north of Lincoln called Risehome, which is full of greenhouses. We're working with Tesco there on ways of digitizing the greenhouse growing process. We've got greenhouses where everything we can possibly sense is getting sensed by these embedded systems, often with Arduinos. That stuff goes into big data systems that are trying to optimize the lighting conditions. Exactly what color of LED light should we shine on the crops to make them grow using the least amount of energy? How do we combine the light from LED lamps with natural light from the sunlight? How do we use LEDs to compensate for cloudy days? If you go to that site at night, all the greenhouses are illuminated in purple because those are the colors of light that make the crops grow, and we want to keep them growing through the night sometimes in experiments. So Tesco are very invested in this. We have a fake Tesco store. We've built a full-size Tesco store inside one of our research labs, and we sense the refrigeration systems. We're trying to build data analytics systems to figure out how to turn the fridges on and off. There's a great application. You probably know when people don't do this as much as they used to. Everyone in the country used to watch EastEnders, and when the commercials would come on, everyone would go and put the kettle on, and there'd be a huge spike in the energy grid, which is very expensive because you have to turn on another coal-fired power station every time there's a commercial break. And so the theory with Tesco is if we can predict when those spikes are going to occur, we can work with Tesco and we can turn off all the refrigeration in all the Tesco stores in Britain for the duration of that TV break, which counteracts the effects of everyone putting their kettles on. But to do that, we've got to sense everything. We're putting sensors in the food on the shelves. We're putting temperature sensors, but also things to monitor the state of the meat, the state of vegetables. We're trying to figure out how this process of turning the power off and on again affects the life of the food. How does it affect other costs, like the cost of transport to bring the food there and keep it fresh and so on. So there's a general trend in computing that the whole world is becoming like this now. Computing has, in the last few years, really gone out of the bedroom and into the real world. Computing used to be about hacking at your desk, and now it is all about being out there. It's about being out in cities. There are sensors in smart cities. I've done work with traffic sensors. We have systems that can monitor the position of almost every vehicle in a city and try and optimize the traffic flows. We can turn the street lamps on and off. We can turn the traffic lights on and off and move people and vehicles around in cities in more efficient ways. There are pollution sensors as part of that. Often that's part of the thing we're trying to optimize. How do we make the flows to lower the pollution? There are sensors everywhere. All these sensors have embedded systems attached. There's things sensing the water. There's robots going down pipes to explore infrastructure. This was done at my old university in Leeds. They're trying to build maps of often very old Victorian plumbing infrastructure with these robotics. Everything's being sensed, shopping's being sensed. We have data from reward cards going into big data systems. We can link all that with the lighting in the road. Should we turn the street lamps on and off in Lincoln at different times because people are moving around? That's controversial in Lincoln because we currently turn them off rather more than in other places. We can monitor people's phones, we know your location. You have a little embedded computer in your pocket which we can use to track you all over the place and predict your behaviors. Everything, the state of the forests, can we detect forest fires earlier? Can we send drones out to monitor things? What kind of computer architecture do you need on a drone? What we're finding is actually a split in architecture now between very small computers that are out in the world like this, in these smart cities or in smart agriculture, and then big computers that live in custom-made buildings the size of factories. These are data centers, compute centers, and they're doing the powerful supercomputing, if you like. And it's because the network enables the data from those small systems to come to the big one. So we're really starting to see the end of the traditional desktop computer. It's split into both of those directions. You're going to do your little computing out in the field, you're going to do your big computing somewhere else, and maybe the device you have to type on is just going to be a very thin client connecting to these computers. I used to work in speech recognition, which uses some of the most powerful computers in the world. These giant cluster machines, tens of thousands of devices working together. And in speech recognition, it's considered cool to pull out the oldest, lowest powered device you possibly can to work on your desk. You have to pull out a mid-90s EPC or something that only has a black and white screen. The implication is that you're obviously not doing computing on the thing on your desk. You're obviously showing everyone around you that you're connected to some giant room with 1 million compute devices in it. And your computer is so powerful that you don't need to carry around a big thing on the desk. A particular application of that sort of computing, you might have heard of deep learning. This is something we're doing here. Deep learning is a fairly pompous name for a 60-year-old algorithm called neural networks, which has not really changed at all in 60 years. But what has changed is the architectures that we run it on. This is actually how I got into computer architecture. I figured out none of the interesting stuff here is happening in the machine learning community. It's all happening in the computer architecture community. It's architecture that is enabling this stuff. When you read these stories about whizzy deep learning people in the media, don't look at them. Look at the people who are designing the computers they're actually running it on, the people they're buying that stuff from. Which is basically the NVIDIA company. They're making very powerful graphics processors, GPUs, that are getting repurposed. So what you have in deep learning are massively parallel computers, such as GPUs. You get away from this whole idea of following one program in sequence, and you're going to run tens of millions of instructions simultaneously in a grid of computing. There's different kinds of parallelism. A GPU is one form. Another form is you just have a room full of 1 million commodity Dell computers, and you run the same program on them all. Or there's more complex kinds of parallel programming that you look at in the third year, where you're really getting the machines to work together in very complex ways. So what's happening in deep learning, you can see there are several layers of computation. These are somewhat analogous vaguely to computation in the human brain. Here you can see an image of a dog. There are layers of computing that extract features at different levels of complexity. Often the first layers in visual system are finding features like edges and corners. And there's tens of thousands of these, and they're all getting done simultaneously in the silicon. At higher levels, you move into more conceptual spaces. First, there's things that are somewhat recognizable, like the presence of noses and ears might come up as features, but then you get into very abstract features like texture, furriness, faceness, gender, animal species are represented at these higher levels. But the important advance here is tens of millions of very simple, small computations all happening together rather than being run in a sequential programming. So if you're interested in this, you'll see a lot of this later on in your course, especially in the third year. I might come back and teach you parallel programming on these kinds of architectures later on. And then out in the field, this is typically the kind of stuff that I work with. There's something out in the field like this with some pretty low power devices. This one's actually got a laptop in it. It's still a low power laptop, but it's doing some kind of operating system based computing as well as a lot of embedded stuff in the back. And then the data is going out into a server room and getting processed. In this case, the machine's learning to recognize weeds in the fields from masses and masses of data. Okay, so I just want to introduce you to the very basic components of a modern computer. we've argued a lot about the definitions of computers. I'm going to leave that for a while and assume that the computer is the thing on your desk again. Okay, so what's a modern computer made of? What's the basic material? Silicon, right? Where does silicon come from? Sand, yeah? So you go out to a beach in California, hoover up some sand, yeah? Turn it into a big crystal, cut it into wafers, yeah? Are they just silicon? No, there's some other stuff. You chuck various other things on the silicon and... Sorry? There's a lot of copper in there for the wires, yeah, yeah. There are agents called doping agents that are used to change the semiconducting properties as well. You have a silicon base, you chuck other stuff on there. And what's the basic structure that we're going to make through that process? It's written in big letters on the slide. Okay, it's a transistor. Okay. So this is a somewhat old-fashioned transistor. This is a transistor that's about that big that you can do with manual electronics. Everything I'm going to look at in this lecture is kind of human-sized stuff. It's things that you can see and touch. So a transistor is the basic element of everything. When we put them on a chip through that silicon process, they become very, very small. This is one big transistor. A transistor is effectively a switch. Think of it like this. This is a piece of plumbing. So you remember the water computer we saw earlier? If you were going to make the water analog of a transistor, this is what it would be. It's a pipe, and you're going to turn on and off the flow of that pipe. You've got a switch up here. If the switch is on, the water can flow. If it's off, the water doesn't flow. Or for electricity, it's the current that's going to flow on off. Actually, already here, you can see some of these ideas about energy, about power consumption. You can see there's a little bit more energy has to go into this than comes out. You're really trying to control this flow. This is the real information flow down here. But what's going to happen to the current that you put into this switch? What you've actually got, imagine this is a fully water system now. Imagine you're going to put in some water at the top and it's going to somehow open a little pressure valve down here that allows the main current to flow. The point is the current you're putting in to do the switching has to come out somewhere. You're using up energy that's coming in on this side of the system to do the switch. And so people now are thinking about how can we recapture that? Where's that actually going? At the minute, it comes out in the same place as all the informational energy going in. But you can see there's fundamentally two inputs to a transistor and only one output. Okay, so you could build a computer out of these kinds of transistors. That was done at a point in history. We could get thousands of these, put them out in a board about the size of this desk. I might show you some video of people actually doing that. You could build a perfectly functioning computer out of actual transistors. But what we do now is we miniaturize them, so there's lots and lots of those. It's 10 with a lot of zeros following it that will fit on a silicon chip the size of your fingernail now. Yeah. Some of these chips still only have a few transistors. If you want to play around with basic chip making, if you want to play around with logic gates specifically, you can buy these on eBay for a couple of pounds. You might get a chip that's got 6 AND gates on it, or a chip with 6 OR gates on it. Usually they package a few of them together. So a chip like that will just have tens of transistors on it, but you're going to have billions, tens of billions on a modern chip. When I was a kid, computers had lots of chips with them. You could open up the BBC Micro and you'd see chips with everything, hundreds of other things, all talking to each other. When you open a modern computer, it's somewhat less interesting. There's a tendency for the silicon to all migrate onto a single chip now. In a sense, it doesn't really matter where you put your logic gates, which plastic package they're in. There's a cost of having lots of chips, as well as manufacturing. They have to communicate with each other on copper wires, connecting the chips together, which is slow. So one of the big trends of the last couple of decades has been everything migrating together. When you open a modern device, especially a mobile device, you're almost just going to see one big chip now with everything on it. Not as much fun as the old days. In the old days, you knew what every chip was doing and you could upgrade chips. There were people competing to make different chips, all migrating together now. So this is the most basic form of computer architecture you're likely to see. This is what happens when you open up one of the desktop machines here in the computing labs. Again, this is almost becoming history now. For a couple of decades, this was what a computer was. It was a standard-sized box, and all the boards and interfaces were standardized. Starting with IBM PCs, everyone became compatible with them. You actually see less of these now because everyone's moving to these embedded devices, things that are going to go out into the world, or on the other hand, they're moving into the server room, into those big compute stations. Maybe this is actually becoming a bit of a relic now, but it's still a starting point to look at other architectures. So your classic PC, usually the first thing you see is a great big power supply. This is not very interesting. This is mains electricity coming in and it's getting transformed into power needed by different devices in the system. The system is dominated by a big green circuit board. That's called the motherboard. Motherboard is like the mothership. It just means the big main board. There can be other boards like the extension cards. So usually the motherboard is characterized by being the one with your CPU on it. It's the one where your processor is sitting. So in a lot of these cases, you can identify the processor because it's the thing that generates the most heat because of this compute process. Because we're putting 2 inputs to every AND gate and only getting 1 out, we are chucking the other one out as heat. And all that heat gets added together and it makes your processor very, very hot. And that's why you have to put a massive fan on it. If you're really hot rodding this, you can use other cooling system. Anyone done water cooling on the machine? Who's the hardcore gamers? All right, that's you. Yeah. The reason you have to do your water cooling is because of that process of computation as heat loss. If you're throwing away information, the information comes out as heat energy. That's why you need a fan. Your fan is throwing information out of the vents of your PC. Okay. The next most noticeable thing is usually the memory. So you can see these are slots and they've got RAM cards inserted. So RAM usually still comes on a bunch of chips. You get a card with a bunch of RAM chips and then you put a series of cards together. And there's a whole load of parallel wires connecting the CPU to the RAM. That's called a bus. Bus just means internal wiring with some protocols running on it. That's the main part of your computer. You've got processing and you've got data. Computing is data plus programs. That's the program execution. That's the data. Actually, it's interesting. In modern computers, we store the programs in the same place as the data. The program itself is in RAM. It's getting executed out here, but we store it in the same RAM chips as everything else. In some computer architectures, that's not the case. In some systems, like in some embedded devices used for signal processing, you'll have a different piece of memory that stores the program, and the data is kept separate. In this kind of architecture, you can, in theory, do really nasty things with programming. You can write self-modifying code. That's a program that changes its own code as it runs because it has access to the same memory where the program is located as where the data is located. So you can do really devious things like writing a loop that just says, do this thing 3 times with the number 3 in the program, but then you can go and rewrite the number 3 in memory and change it to a 2 and a 1 as you go down. Not usually advised as a team working programming style. You can really confuse people. Good for security applications if you want to really confuse people, writing self-modifying code. Okay, so beyond the basic processor memory bus structure, you see various peripheral devices. So here are several expansion cards. These are plugging into various types of slots. Anyone know the names of these kinds of slots? PCI, PCIe, yeah. There used to be AGP for graphics. So there are various different protocols for how you connect things from outside into the bus system of the computer. So these cards are typically things like your graphics cards. In the old days, you'd have a whole card for networking, a whole card for sound. Again, a lot of these functions are now migrating onto the same silicon as everything else. Yeah, this shows the age of it. Then you've got masked memory. So look, there's a hierarchy of memory. There's a little bit of very fast memory stored on the processor. Those are called the registers. There's probably a kind of memory called the cache, which sits in between the processor and the RAM. Then there's the RAM, and then you've got really big, slow memory in the form of something like a CD drive or a USB stick plugging into the system. That's for your bulk storage. So this is a concept of memory hierarchy. You can have memory that's small and fast or big and slow, and a modern computer usually has a whole set of levels in that hierarchy. Okay, so let's zoom in a little. This is still stuff you can see with your eyes, touch with your hands. These are the components of the motherboard itself now. We've taken the CPU and the fan off, so you can see there's a socket here. That's where you put your CPU. It's characterized by there being lots of pins. CPUs have lots of inputs and lots of outputs. Okay? Most of those are used for addressing. If you have a 64-bit machine, that means you can address a 64-bit memory space, which means you need a lot of wires going out with zeros and ones on, saying which bit of memory you want to talk to. Okay. So in this one, we've got the slots labeled. This one's got a PCI and an AGP. That's a slightly older graphics card slot. You can see there's something called the memory controller here. That's sitting between the CPU and the RAM, handling the transfer of data between them. You can see there's still a few smaller chips sitting around. Let's look at what a few of these are for. You'll find things like an I/O controller. Everything to do with input-output has been put on a separate chip. Nowadays, you'll find things like the sound card might have migrated onto the motherboard. The sound card used to be a thing you plugged into a slot. Now, usually the sound card's going to sit somewhere on here. That might have its own chips. Again, on a really modern machine, that'll all migrate onto a single big chip along with the CPU as well. There's the RAM banks. You can see there's lots of connectors here. Most of these connectors will have some protocol, and that protocol will be handled by some small chip that is acting as an interface between the main bus system and that particular protocol. You see there's some connection with the real world, something like a audio microphone port. That's probably got converters from analog to digital sitting there. Maybe some basic signal processing could be done here. If you're playing music, you might have your graphic equalizer done in hardware to take the load off your CPU. Okay, so for a long time, at least, that was the conventional view of a standard PC. There's probably more laptops are being sold than desktops now. There's a lot of laptops in here, I can see today. So inside these boxes, you probably have something that is basically the same structure, but a little more compact. It will probably have different choices of components that are optimizing for physical size and for power consumption over pure performance that you still find in the desktops. So let's try and identify some of the components here. You can see again we have a processor sitting here. You will find the RAM. Usually the memory is easy to find because it's a big homogeneous area. Right? RAM is big, there's a lot of it, it's all the same, it's homogeneous. So you can see this is a bank of RAM sitting over here. What else can we find? There's some audio stuff happening here. There's stuff that is controlling the specifics of the laptop, so supplies for the lighting in the laptop, the specific devices on that laptop. Stuff around the edges, you see there's a lot of things to do with power. There's different kinds of power supplies. Different parts of this are running at different voltages, which have to be transformed. There's a clock. The clock is very important. That sets the timing of everything else. But it's basically the same structure. Of current interest in these is a secure boot system. So we're still struggling with this ongoing war against university administrations letting us run Linux on our stuff. And there's this cat and mouse game where certain companies that make proprietary operating systems try to prevent people from doing this. So for a long time it was all done in software, and you could circumvent the security measures at a software level. What we're getting now from institutions like universities is they're trying to lock you into an operating system at the hardware level. So as I was saying about architecture as security, if you want to circumvent something like a secure boot system, you now have to go down to this architectural level. So secure boot is going to do something in hardware that controls the boot up sequence of your computer. It's not going to let you have access to the parts of the hard disk that you used to have access to. But that process has to exist somewhere in the computer at an appropriate level. If you find that, you'll find there's a chip in here that is monitoring the secure boot process. That chip comes with a factory reset system. So if you lose your password and take your computer back to the seller, they're going to do something to reset it. So you'll find there's two little pins on that secure boot chip that can be used to reset it. So if you need to get rid of a proprietary operating system, you might need a microscope and some tweezers and stuff now. It's all getting a bit small and fiddly. But if you hotwire those pins together, you can get rid of your proprietary operating system by knowing where that chip is in there. Not that I would ever condone doing that on a machine on the university network at all. Okay. So this is an example of this process of silicon migration then. What we're now seeing, this is a Raspberry Pi. Anyone used a Raspberry Pi before? Yeah, good. So Raspberry Pis are somewhat less interesting now than they used to be. They used to be small, low-power computers that were interesting because you had to do different architectural things with them. They've actually got so powerful now that they're behaving pretty much like a regular desktop for a lot of purposes. So the architecture is less interesting. But they're a nice example of this migration. What you have here is not lots of small chips. There's really just one big chip. This is called a system on a chip. System on a chip means not just the processor, but a whole bunch of things that used to be on other chips have all got miniaturized and put on there. What you will typically find here is that part of the design of that chip is the processor, known as a core, or IP core, intellectual property core. Most of them are designed by the company ARM, which is based in Cambridge. If you want to work there or do an internship there, it's a great place in the UK to do computer architecture. So ARM don't make chips. They're really a software company. They sit in an office with computers and they design things on computers. And they sell those designs to people who do make chips. So there's lots of different people manufacturing chips that include the ARM design as parts, often of something bigger, like these system on the chips. Okay. So there's memory sitting on that chip now as well as the processor. There might be memory sitting somewhere else. You can see there's still a couple of things that are to do with input-output control. So this is a USB hub that's sitting on its own chip. There's some kind of camera interface here sitting on its own chip. But pretty much everything else is now migrated into that one place. So again, it's kind of less fun. You used to be able to do computer architecture by opening up your BBC Micro and you could see the architecture. You could see what was on which chip and how they were connected. You don't really have much chance of understanding what this is doing now. There are people who, if you boil that chip in acid for a while and then photograph it under a microscope, you can get a picture of the chip layout and try and figure out what it's doing. But the architecture is less clear now than it used to be when it was something you could hold in your hands. I mean, this is a fascinating trend. I'd have never believed this when I was a kid, that computers now take up more space, so connectors now take up more space than the computer. So there's recently been this fiasco over headphone jack standards. The Apple company is trying to replace the conventional headphone connector with something smaller, because the headphone connector is now the biggest thing in the computer, which is just completely crazy. If you're used to a computer being something that sits on your desk, and now they're arguing about a headphone connector being the size bottleneck of everything, that gives you an idea of how everything is shrinking down now. So this is what it's shrinking to. This is inside my phone. Not very different from what you find on a Raspberry Pi. Again, we can see one big chip here. This is a system on chip. Again, it's got an ARM core sitting on it, but it's also got a whole bunch of other stuff. In this case, the system on chip you can see is designed by Samsung. It's got Samsung's brand stamped on it, but it's using ARM IP as part of the design of that. So you can usually spot the processor. It's the big thing, and it will look like it's in the middle. If you look at a map of a country, you can find the capital city, because it's where all the roads are pointing. You can usually find the processor, because it's where the roads are pointing. The processor is like London, and the RAM is like the industrial north, where a lot of the real but less glamorous work is being done. And it's moving back and forth between the RAM and the processor. On a mobile phone, you'll find some more specific things. So these behave more like an embedded system. It's more like the kinds of chips you get in these smart cities and things with lots of sensors on them. So you'll find things like a pressure sensor, biosensors, temperature sensor, inertial measurement unit. These are the things that understand the physical position of your phone. If you want to play games using the phone to wave around like Just Dance, that'll have an IMU, initial measurement unit controller in it. There's a lot of stuff here to do with networking. So there's a specific chip here, I think. This is a Broadcom chip for managing Wi-Fi and radio comms. That's still sitting on an extra chip. But the core of it is now all sitting on that little tiny bit of silicon there. One of the things we'll do in the workshops is take your favorite computing device and find out what all the parts are like that. So if you have a favorite device, bring it in. You don't necessarily have to take it apart with a hammer. You can just look it up on the internet. But taking things apart is quite fun if you manage to put them back together again. Okay, so especially for game students, games consoles are also computers. This is something I just bought, it's a Nintendo Switch. Again, back in the 1980s, console architectures were interesting. Every console had its own particular features, its own particular chips. Some of them had particular systems that could do software scrolling really fast. There were tricks you could do about setting pointers to memory for screen display that enabled you to shift the content of the screen from left to right without actually moving stuff around in memory. That's called hardware scrolling. And it gave rise to a whole bunch of games that were characterized by very fast horizontal motion, like Sonic the Hedgehog. What you find now is, again, somewhat less interesting. I was really disappointed to find that this proprietary custom Nintendo I bought was actually just another ARM core sitting on another system on chip. It wasn't actually that different from all the other ARM cores I've got in my house already. There's nothing specifically Nintendo-ish about it anymore. Again, you can see the basic structure. Here's the RAM. The RAM is like the industrial north. It's a big homogeneous place doing unglamorous but real work, and here's the processor doing the glamorous work like London, and here's the buses connecting them. What's somewhat interesting about the Nintendo is that this chip is not made by Nintendo, it's made by NVIDIA, which is really a graphics company, it's a GPU company. So what they've done on their system on chip, instead of focusing it on the ARM, they've started with a graphics card, they've started with a GPU. So this thing has got lots and lots of GPU cores on it, and the little ARM CPU just chucked in there as well, but it's primarily a graphics processing chip. We're actually seeing here maybe the end of the notion of the CPU as the focus of a machine. It's the first time that the graphics card has really become more important than the CPU. The CPU is just there to coordinate what the graphics card's doing, but this is fundamentally a GPU with a little tiny ARM CPU bolted onto it. Okay. This is a good question about what is a computer. Is this a computer? This is what's inside my router. Is a router a computer? Yeah? So again, what's here? This is the same thing again. Here's another system on a chip. Again, it's got an ARM core. It's running at 333 megahertz. There's some memory there. There's a bus connecting them. So these things are full-on computing devices. Now, when you think about it, your router's running a little web server. When you log onto the config page, you're seeing an HTML site, and that's being served by a web server. That's the same kind of web server running in any web server. But some of these can be hacked to let you serve your own web pages just off your router like that. So this is interesting from the point of computer security again. A lot of people will spend much time securing their computers, but they forget about their router. They might have a home router that's been there for many years. There's currently a lot of controversy about Huawei Chinese routing equipment, which has this stuff, and people are asking security questions about governmental control, as they do in other countries like America, where the NSA has been accused of putting things into American-made routers as well. So again, by knowing a bit of architecture, you can look for these possible security holes in places you might not think of. Is your TV a computer? Yeah? Okay, this is what's inside my TV. There's the same structure, big system of chip. You can see MediaTek is the company that makes the system on chip, and ARM is the company that's made the IP core, the design of the CPU on it. Yeah, so my Sony TV is running an operating system, and it came with a paper copy of the GPL, the GNU public license, which is required for running Linux coders. It's the first time I've ever seen the GPL on paper, and especially in a consumer product. So yeah, your TV is running an operating system. It's a full computer now. You see the design of this is going to include somewhat different things. So this is a computer that is specialized pretty much just for decoding and display of video data. So probably this system on a chip is going to have a lot of specialist stuff that is to do specifically with video codecs. It's going to have hardware implementations of MPEG decoders and OGG decoders and all the media files that you would otherwise do in software on a desktop computer. How about your washing machine? Is your washing machine a computer now? Yeah? So this is inside my washing machine. So this is a PIC, which is an embedded processor. I've not actually tried this. You probably could hack that. If you had the right connector to upload new firmware, you could probably upload stuff to that and reprogram it and maybe get it to play Space Invaders. If you can figure out the position of all the LED lights on the washing machine. Interesting exercise for you. Okay. So, that was a bunch of examples of computer architectures. They're all characterized by this structure then. There's always the CPU, until we get to the Nintendo, at least. This is the classic architecture. There's the CPU. You have memory. That's those banks of RAM. You've got I/O devices, sound cards, video cards. And then you've got buses connecting them all together. The buses are the wires between them and the protocols running on those wires. So for a long, long time, probably longer than you think, this has been the standard architecture for our computers. There was a computer design like this from 1835. This is how the Charles Babbage machine looked. And we'll explore that in more detail next week. The Babbage engine is remarkably like a modern computer. It's so much like a modern computer, I'm going to use it to teach you how the modern computer is made. You can see all the parts as physical cogs driven by steam, but what they're doing is exactly this modern architecture. Okay? So, architecture is all about hierarchies. That means we can zoom in and we can zoom out. And this whole module is going to be looking at levels of hierarchy. You've got to understand where each lecture fits into the hierarchy. Each lecture is going to be about one level. It's going to use components that are smaller from previous lectures, and it's going to form a component of the next lecture. So you've really got to understand how this fits together. This is the fundamental organization of it all. So that's your kind of human visible level. This is what you see on a motherboard. Okay? But we can zoom in on one of these components. Let's take the CPU. Okay? So we can zoom in on the whole CPU. And we'll see a similar structure again. We'll see there's something called the arithmetic logic unit, or ALU. This is the bit that is like a calculator. It does the adding. Sometimes you tell a CPU to do some adding, please. And that part of the CPU will do the adding for you. But there's other things on the CPU as well as that. So you have registers. Registers are little bits of memory that are on the CPU. You bring data out of RAM, you put it in the registers, and then you tell the arithmetic unit to do some adding on the stuff in the registers. Usually it'll store the result in another register, and then it's another job to send that back out into RAM. There's something called the control unit. This is the bit that manages the execution of the program. So your program isn't just adding, it's adding in a sequence of steps, and the order you do those steps, the program, is something that is determined using logic. So if you have an if statement, you say if something is true, if something equals something, if something is greater than something. You need logic here to manage that process. So for example, we might bring in two numbers into the registers, we might add them together with the ALU, we store the result somewhere, and then we say if the result was 0, go to somewhere else in the program. Okay? You're allowed to use goto at this level. You're not allowed to use goto in regular programming. This is the level where goto still exists. So that addition is done here, but the if is a control. That's part of program control. That's done in the control unit. Okay? And then you have buses. These are different buses that exist within the processor. So in a classic computer, the processor was one chip. RAM was outside. You'd have these little buses inside the chip. And the bus at this level would be the copper wire on the motherboard connecting the processor to the RAM. Okay? So again, we can zoom into this stuff as well. So we might take the arithmetic portion of the chip. So technically an ALU is a specific type of arithmetic unit that is to do with integer arithmetic. If you're doing floating point arithmetic, everyone know what floating point is? The non-integer numbers, 3.8 times 10 to the 6, those kinds of numbers. So you'll typically find floating point arithmetic is done by a different part of silicon called a floating point unit. Often this doesn't exist on embedded systems. It's something you have to work around. You have to do everything with integers in embedded world. That's distinct from the arithmetic logic unit. That's the standard symbol for ALU. Don't know why it's that shape. It's traditional. Okay, we can zoom in again. Let's take that ALU and zoom in on it. We'll see that is made out of logic gates. Okay, so you might have studied these at school. This is and or and not. Now, logic gates aren't real. You can't look down a microscope and see a logic gate, but you can look down a microscope and see the transistors. Okay? These logic gates are the abstract entities that are made out of a handful of transistors. Four or five transistors. Some people who really work with this all the time can just about identify a logic gate. If you zoom in on a chip in a lot of detail, you can see the transistors. You might occasionally be able to recognize that little cluster of transistors that together form a logic gate. But when you write a logic gate on paper or when you make one in a simulation, just remember it's actually a notational shorthand for a small collection of transistors underneath. Okay? You can zoom right in and you can see the individual transistors and the parts of the transistors. This is the level of actual silicon. This is a real microscope photograph of little bits of silicon and non-silicon that's been zapped onto the silicon to make the transistors and the wires connecting the transistors. Okay, we can go the other way. So again, we start in the human world of motherboards and boxes. If we zoom out, increasingly today we see that what used to be called our computer is now just a component of a much bigger system, which is arguably becoming the computer. If you're doing parallel computing, especially working in data science, big data, your computer is this thing that fills a room, and it's made of millions of boxes, which used to be called computers. But in practice, the whole thing is acting as one big computer now. There are weaker forms of that. Parallel computing can also be done over the public internet. There's been projects like SETI at home, where they take a big computation and just send out little packets of it over the net. So again, a trend of the last couple of decades has been, again, what is a computer? Is it one box or is it a million boxes plugged together? What's the right level to think of? Somewhat out of scope of this module, when you do your networking module, you'll see structure in here again. There's the concept of a network as opposed to the internet. A network is a bunch of computers in one office or one building wired together. The internet is when you take those networks and wire them all together to talk to each other. And there are different levels of hierarchy that can exist up there as well. Okay? This is just to remind ourselves, think of physical architecture as a metaphor for everything we do here. In physical architecture, there are different philosophies. This is a cathedral. This is Lincoln Cathedral. Some people like architectures that are like this, this is clearly designed by one person, at least one person at a time. There's clearly someone who was in charge of this, who's planned it. You can tell that because the structure is very symmetrical. You can tell, and objects here kind of reflect each other, and they're all positioned very well. When academics design architectures, when academics do chip design, this is the kind of architecture they make. They make something really beautiful and correct and pretty, okay? When Intel designs architectures, they're a total horrific mess because they've evolved over nearly 50 years, and they try to retain compatibility. If you run a program written for a 1980s Intel chip on a modern Intel chip, they've designed it to keep all those instructions there. So what you find on an Intel chip is kind of things piled on top of each other. If you've ever seen these old buildings, there's a few in Lincoln that were built by the Romans, and then someone's knocked half of it down and built a new thing, and they knocked that down and put a concrete thing on. That's more what a commercial current chip will look like, because they've not been designed from scratch. They've been extended over many decades. Keep computer architecture distinct from other kinds of architecture. You might hear job titles like data architect, software architect, systems architect. That's not what we're doing here. Those are software roles, often commercial job titles. Computer architecture is what we're doing here. It's the study of hardware. You might also hear organization or computer organization used distinctly from architecture. I actually don't make much of a distinction here. In all the books, you might see titles like computer architecture and organization. In the old days, it was much more common for programmers to work at assembly language level, and the interface of the computer would be the assembly language implemented by the processor. If you were an 8-bit video game writer, you would see the architecture. So at that time, architecture was used to describe designs that a programmer would see. It's all the external facing stuff, like the design of the assembly language, the instructions in the language. And it was seen as the API, it was the interface between the hardware and the software. Whereas organization was how you implemented that. Organization was about the logic gates and transistors and the best way to get those instructions actually executed. So there's less of that distinction now because fewer people program at that level. Everyone now is programming sitting on top of an operating system and libraries, and so most programmers don't see either of those things, and therefore I'm going to subsume it all into what I call architecture. But some of the books I recommend will make more of that distinction. Okay? So, just a quick tour of the rest of the module again. Next week, we're going to do history. We're going to start in the Stone Age. We're going to go through the Steampunk Age, Charles Babbage, the original steampunk. And then we're going to look at the history. Okay? We're going to look at data representation. That's about zeros and ones and hex. We're going to look at logic. We're going to look at CPU design. If you only come to one lecture, come to this one. This is the heart of it, lecture 5, the CPU. We're going to look at memory, buses, embedded, parallel, performance, and the future of computing. So, I look forward to seeing you all next week. Thank you. Thank you.